We'll make a start. I'd like to thank Fiona O'Connor from the Met Office for coming to talk about Earth system modelling. Fiona.
Thank you, Luke. Can you hear me okay? Brilliant. Thanks. Thumbs up from the back. So my name is Fiona O'Connor from the Met Office Hadley Centre. I joined the Hadley Centre in 2004, and that was really at the very beginning of UKCA. And then that composition component then became integrated into the Earth system model. And I'll talk today about what we mean by an Earth system model and give you an introduction about Earth system models, the development of climate models over the past decades, and why including Earth system components within those models is important. So in terms of what I'll present, I'll first of all explain what we mean by the Earth system. I don't think that should come as a surprise to you. And what do we mean by an Earth system model? I'll then talk a little bit in terms of motivation about why having components of the Earth system is important in the context of climate change. And then I'll talk a little bit about the development of models from either atmosphere-only models or ocean-only models right through to full Earth system models. And I have one slide in there that explains the kind of hierarchy of models that exist when we're looking at atmospheric composition. So it's really just to give you a feel of the different complexities of models that address questions of composition and the terminology associated with them. I'll then move on and talk a little bit about the UK's current Earth system model capabilities. And obviously that's constantly evolving. So I'll talk about the existing models, but also plans for the next version of our Earth system model. And then I'll finish up with some recent Earth system highlights that fed into the sixth assessment report of the Intergovernmental Panel on Climate Change. Okay, so what do we mean by the Earth system? This is a schematic which was used to represent the UK's first Earth system model, HADGEM2, and in fact it was the first Earth system model that included UKCA composition. So effectively the Earth system is made up of a number of spheres like the atmosphere, the hydrosphere, the biosphere and the geosphere, and it's considered a system because each of those spheres is interacting with the other spheres. It includes the cycles in relation to nutrients like carbon and nitrogen and how they exchange across the different spheres. But it also includes aspects like the hydrological cycle and deep earth processes. And as I say, it's considered a system because each of the components within that system are interacting with other components. Indeed, life is also part of the Earth system. This may be life on the land, but equally in the ocean. And indeed, humans themselves are part of the Earth system. And one could argue that humans and our activities are driving unprecedented change within the Earth system. So this is really the kind of scope we're trying to include in Earth system models. So that's a lot of complexity, a lot of processes, and a lot of interactions. Okay, so how is Earth system science relevant to climate? So the first example here I'm presenting is from a paper published in 2020. It's looking at changes in the abundance of ozone in the atmosphere over the historical period relative to the pre-industrial. So this particular slide goes from 1920 through to the present day, and the changes plotted here are relative to the pre-industrial period at 1850. And what you'll see is that the abundance of ozone over the historical period is increasing, and at the present day it's causing a perturbation in the Earth's radiation balance of about 0.3 to 0.4 watts per square metre. So I tried to put this into context because 0.4 watts per square metre, what does that really mean? So I worked out that it's equivalent to a 3-bar electric fire running all day, every day, over the area of a football pitch. So of course, if you imagine how many football pitches might cover the globe, that's a lot of football pitches, a lot of electric fires, and a lot of extra heat that we're adding into the Earth system, and that's solely due to changes in ozone abundance over the historical period. And of course, calculations like this are only feasible by including interactive chemistry within a climate model. So that particular figure was showing the evolution of ozone changes over the historical period. This bar chart here has been taken from the IPCC 6th Assessment Report published last year. And here on the left, it's showing how the changes in different emitted species over the historical period have influenced that Earth's radiation balance. You'll see that ozone isn't listed here, and that's because ozone itself isn't emitted directly into the atmosphere, but it's formed in the atmosphere from other emissions. So the green bar, the portion of these bars that is coloured in green, is the contribution from ozone. And so if we were to add up these different bars, and you'll see that some of them are negative. This is because of the stratospheric ozone hole caused by chlorine species. But you'll see there are positive contributions from volatile organic compounds, from methane. And of course, if we add up these green components, we will match what we saw in the previous slide. So you'll see from this slide that CO2 and the changing emissions of carbon dioxide over the historical period is the single largest driver of changes to the Earth's energy balance. Second to that is methane, but you'll also see that there are emitted species that form aerosol in the atmosphere or are emitted directly as aerosol, are offsetting some of those positive perturbations to the Earth's radiation balance. And of course, we can only quantify these contributions through having models that include both interactive chemistry and aerosols. So again, this is another reason why we're interested in including aspects of the Earth system within climate models. This next example is very much out of my domain, but it's focusing on carbon dioxide, which you'll have seen from the previous slide is the single largest contributor to climate change. So this schematic on the left is really showing where do the CO2 emissions come from, and what happens CO2 once it's emitted into the atmosphere. And the schematic on the right then is just showing the budget of carbon dioxide between the land, the atmosphere and the ocean. So first of all, if we consider emissions, about 90% of the CO2 that we emit into the atmosphere is from burning fossil fuels and from cement production, and about 10% is through land use change. And of the emissions that we emit into the atmosphere, about 50% of the CO2 that we emit remains in the atmosphere. And that's what we refer to as an airborne fraction. And of the remaining 50%, about half of it is taken up by the biosphere. So in particular, plants and trees are taking up carbon dioxide from the atmosphere and using it for food. And about a half of that 50% is being taken up by the ocean. And there is concerns that this airborne fraction might change and is sensitive to both carbon dioxide and temperature. And of course, if that does change, in particular if the airborne fraction was to increase, that means we would get even more climate change per unit of emitted CO2 than we currently are. So it's really important to understand how this airborne fraction might be sensitive to temperature and CO2. And this is what's shown in the next slide. So again, this slide here has been taken from the 6th Assessment Report from the IPCC published last year, and effectively is showing the response of both the land and the ocean to both changes in carbon dioxide and to climate. So, for example, if we were to look at the land carbon response to carbon dioxide, what we're seeing is that as CO2 increases in the atmosphere, the trees quite like CO2, so they will grow more, and that acts to reduce the airborne fraction and hence would give rise to a lower radiative forcing per degree. In contrast, if we look at the land carbon response to climate, as climate warms, there's more respiration, so more release of CO2 into the atmosphere, and indeed climate change might have changes to the hydrological cycle associated with it, so there may be a lack of water availability, and effectively then climate is driving an increase in the airborne fraction, and hence why the sign of this is positive. But overall, it looks like the overall feedback is negative. So again, calculations like this are only feasible by including an interactive carbon cycle within models. And you'll see there's still quite a range of uncertainty in these estimates, particularly in relation to the land response. And that's a key part of research in the whole sphere of the terrestrial and ocean carbon cycles. The other reason we're interested in including Earth system components within models addressing climate change is because we can use them as tools to provide advice in relation to mitigation options and policy advice to government. This is a schematic that was published as part of a global methane assessment last year and very much underpinned a methane pledge that was announced during the United Nations Climate Conference that was hosted in Glasgow last year. And as part of this assessment, they've assessed the feasibility of emission reductions from different sectors and including some additional measures that aren't directly targeting methane, but may give rise to emissions reductions of methane through other measures. And what they've quantified here is the amount of warming that might be avoided, the number of premature deaths that would be avoided through methane-driven changes in surface ozone, likewise the number of hospital visits avoided, and indeed also ozone damages crops. And so they've also quantified the impact of the reduction in surface ozone and what that might do for crop productivity. And you can see that the projected avoided warming, if they were able to implement feasible measures in agriculture, waste, fossil fuels, and these additional measures, which I think would account for something like a 45% reduction in emissions, there's the potential for avoided warming of about 0.28 degrees. So again, this very much underpinned the announcement of the methane pledge at COP26. So again, this kind of assessment is only feasible by including aspects of the Earth system with some comprehensive analysis as well. Okay, so I hope that's kind of set the scene as to why we're interested in modelling the Earth system, how we apply it in the context of climate change to provide both mitigation and policy advice. So over the next few slides then, I'll talk briefly about how models have developed over time. So this is quite an old slide now, but I've taken it from UKCA in Boulder, Colorado. And it shows from the 1960s how models have evolved over time. So to begin with, models very much were either atmosphere only or ocean only. And then it was really in the 1980s that they started to couple the atmosphere and the ocean together. They started to add in the representation of sea ice. And then you'll see it was in the 1990s where they started to include aspects of composition. And they included sulfate aerosol because it's probably the single most important aerosol in terms of offsetting greenhouse gas warming. And of course, it was also relevant to things like acid rain as well. And you'd see beyond that then things like interactive vegetation and carbon cycle started to be included. And indeed, atmospheric chemistry there is listed as being added in the 2010s. In the case of the UK model, HAGEM 2, I think, was frozen about 2010, I think, ahead of the fifth phase of the coupled model into comparison project CMIP 5. But of course, even now at the present day, there are still some Earth system models that would have contributed to the sixth phase of the coupled model into comparison that still aren't including aspects of atmospheric chemistry. You'll see there's ice sheets included there, but the reality is that the global Earth system models that contributed in CMIP 6, there wasn't a single one that started that had interactive ice sheets. But that's something that is currently changing. So we anticipate for CMIP 7, for example, that some of the Earth system models will include interactive ice sheets. And ice sheets are incredibly important in terms of sea level rise and the potential for irreversible changes within the Earth system. So although that figure shows the kind of evolution in modelling, in model development, it doesn't really tell you anything about the complexity of the different components. And this is what's illustrated in this plot, where the different heights of the cylinders are representing now the complexity of representation in the different components. So again, you'll see, as well as in adding in additional Earth system components over time, the complexity and representation of the different components themselves have also evolved over time. And so I thought it would be useful to include in this slide, which is kind of showing the hierarchy of models that are available to us when we're interested in something like atmospheric composition and how that relates to Earth system models. So over here in the bottom left is probably the simplest type of model that you might have in studying composition and chemistry. And indeed, yesterday you would have been using a zero-dimensional box model in your first experience of using UKCA. One could imagine then, if we wanted to add some additional complexity, so this particular box model here is kind of static in its location, and you're modelling processes over time, adding in some photolysis and some emissions, and you're modelling the composition over time. But the box itself is static in terms of its location. So one could imagine then, let's calculate the trajectory that a parcel of air might take in the atmosphere. So now we have a trajectory, and this arrow here is representing the flow in the atmosphere. And let's run a box along that trajectory. And so that box is now moving in space. And how does that influence the composition within that box? Because now things like the pressure and the temperature are evolving over time. And we refer to that as a Lagrangian model. The next, oh sorry, that's gotten off my slide, the side. That's a bit odd. Sorry, I was moving these around last night actually, so apologies. So the next level of complexity, if you like, in terms of modelling composition is what we refer to as a chemical transport model. So here, where before this arrow here was representing the flow of a particular parcel through the atmosphere, here these arrows are now representing data flow. So we have some offline fields that are representing giving us information on winds and temperature and so on. We can feed that into a model that then is calculating the dynamics and the advection of some chemical tracers. And then, of course, we can solve for the rate of change of different chemical tracers. And this is what we refer to as a chemistry transport model, because the dynamics and the advection are kind of predefined, if you like, through these offline meteorological data. The next step up from that is what we refer to as a chemistry general circulation model. And I should say this schematic of these three different types of models has come from this paper by Paul Young. So the difference here in this general circulation model is that now the model isn't getting its meteorology from an external source, but is actually generating that meteorology itself. Again, we're calculating the dynamics and advection, and that's driving the chemistry. But in this case, the chemistry has no influence on the meteorology, because we have no link here between the chemistry and the radiation. And the radiation scheme is kind of seeing prescribed chemistry, and it's these prescribed chemistry fields that are driving the radiation and the dynamics. And the next level of complexity is then when we make this link between chemistry and radiation. And although it's labelled here as chemistry, it could also mean composition. And so what this means is that changes in composition, be it trace gases or in the aerosol phase, are allowed to perturb the Earth's radiation balance, and that then affects the dynamics of the model itself, and it's all interconnected. And of course, these are only referring to composition, but of course we can then implement it within a full Earth system model, where we might have linkages with the biosphere through interactive emissions, and of course interactions with clouds and so on. So hopefully this gives you a feel of the kind of hierarchy of models that are available to us and that we use within Earth system science. The other key aspect of an Earth system model, where you have something like composition embedded within an Earth system model, is that you end up being very susceptible to biases that are driving the component that is of interest to you. So this is an example of biological activity in the ocean, and we're showing here surface concentrations of chlorophyll, both in the winter and in the summertime. And biological activity in the ocean will be dependent on temperature, it'll be dependent on nutrient availability, on light, and indeed it'll be dependent on the transport and advection within the ocean and mixing. So the performance of an ocean biogeochemistry model will be very sensitive to the physical and dynamical processes that are occurring in the ocean itself. And so an Earth system model is only as good as the underlying physics and dynamics. So we're susceptible to biases in the mean state, but we're also susceptible to biases in variability. And the figure on the right is just showing that in the ocean there can be variability at sub-seasonal scales, which again can drive changes within an Earth system component like ocean biogeochemistry. So moving on to the atmosphere, I've taken an example from a PhD student of mine, João Teixeira, who's published this paper in GMD last year. And he's implemented a fire emissions model within our land surface, and he's coupled the emissions from that fire model to UKCA. And this particular plot then is showing the Earth system model plus the fire model, which is conveniently called Inferno. And here we're showing a distribution of the diagnosed burnt area from that interactive scheme. And on the left-hand side is the equivalent in terms of observations. And what you can see, for example, over Africa, there's an underestimation of the fire and the burned area relative to the observations. And we've attributed that low bias to an overestimation of the tree fraction in savanna biomes. And indeed, the fire spread amongst trees is lower than would be associated with savanna, and hence the fire doesn't spread, and so we're getting an underestimation. And again, it indicates that when you include more complexity within your Earth system or include a new component, that you are very susceptible to the underlying physics and dynamics. And in this particular case, we're very sensitive to the vegetation that the dynamic vegetation scheme itself is modelling in terms of its vegetation. So when we replace the modelled vegetation distribution with that from observations, we end up improving this negative bias here. Okay, so over the next couple of slides then, I want to talk to you about our current Earth system capability that we have within the UK. So I mentioned HADGEM2, which was a model we developed and froze in something like 2010, and that participated in the 5th coupled model into comparison project. Well, this next Earth system model, UKESM1, was a joint development between the Met Office and the academic community, and we used that. I think that was I can't quite remember. That was probably frozen in 2019, and was used to contribute model simulations to the 6th phase of the coupled model into comparison project. There's been an intermediate version released just this year, 1.1, addressing some of the deficiencies, if you like, in version 1, and then development is underway for this second version, which will be frozen, I think, in about 2025, and we will use in CMIP 7. So over the next couple of slides, I'll just indicate a little bit about those models. So this is a schematic here showing the different components within the UK's Earth system model, and this is version 1.0. And the blue boxes here are showing what we consider to be physical components. So for example, there's an atmosphere based on the Met Office unified model. There's a land surface model called Joules. There's a sea ice model and there's an ocean model. You'll see UKCA there is split between green and blue boxes. This is because the aerosol component of UKCA is considered part of the physical model, whereas interactive chemistry is considered an Earth system component. And it includes here Medusa, which is the ocean biogeochemistry. So this model is well documented now in the literature. So for example, the atmosphere component of the model is described in this paper by David Walters. The coupled model equivalent, where the atmosphere and the ocean have been coupled together, is published in that paper by Keith Williams. The aerosol component has been published in a paper by Jane Mulcahy, published in 2020. And the interactive chemistry was published in a paper by Alex Archibald and others, and I know he presented to you yesterday on the chemistry. And the full Earth system itself then is in a paper published by Alistair Seller in James in 2019. Okay, and you'll see bicycles is the ice sheet model, so that never made it into UKESM1, but the developments have very much matured, and the aim is that that will be included in version 2.0. Okay, so with UKESM1, we found that there was a temperature bias over the historical period relative to observations. So the observations here in this slide are in black and green. This slide is covering from 1860 through to the present day. And the UKESM1 model is shown in blue. And what you can see is that as the aerosol abundance in the atmosphere increased, it drove cooler temperatures, and we refer to this as a pothole. And so over the last year, Jane Mulcahy and others have tried to improve UKESM1. In particular, they've improved the SO2 dry deposition, so they've reduced the aerosol loading a little bit in the atmosphere. They've reduced the magnitude of the aerosol forcing, and they've included some bug fixes and retunings. And now in red is version 1.1, and you can see that they've reduced the negative temperature bias in this pothole by about half. There are equivalent plots on the right-hand side, except where on the left it's looking at global mean quantities. On the right, then, it's looking at the northern hemisphere, where, of course, the impact of aerosols on temperature would be even more exaggerated than in the global mean, because of the dominance of land and emissions in the northern hemisphere relative to the southern hemisphere. And you can see further details in this paper that's currently in discussion in geoscientific model development. Okay, so that was UKESM 1.1, so that was a small improvement beyond what we used for CMIP 6 with 1.0. And as I mentioned, there are now developments underway in order to produce version 2.0 of this Earth system model. So the kind of improvements that will go in, I mentioned ice sheets already. I mentioned interactive fires. So the example I showed was where fires were coupled to UKCA, but they've also been coupled to the carbon cycle and the terrestrial vegetation. So the aim is that will become part of UKESM 2. There's improved stratospheric ozone in there, mainly from developments from here at Cambridge. And also we've developed this new capability where instead of prescribing the concentration of methane in the atmosphere, we're now driving with emissions. And this is very much a new capability that we're quite excited about, and allows us to do much more policy relevant advice. I thought it was worth including in this slide, in this presentation, an example of a kind of decision tree, because hopefully by now you realise actually Earth system models are complex. The scope of the different components is enormous, and indeed the level of complexity that you might put into the model again is as long as a piece of string. So how do we decide whether we put something into the Earth system model? So this is an example of a decision tree that we've put together in order to determine, what work we might do in relation to the Earth system model and what we would include and what we might exclude. So one key question is whether is the process important in the context of climate change? Is it addressing a key scientific question, a key knowledge gap? Is it relevant to policy? And if the answer to that is yes, do we have the relevant expertise within the UK to develop that component and that capability? And indeed, if the answer is yes, then is the model component good enough? Are the developments themselves mature enough? Has the code itself been written in a robust way? Has it been reviewed and documented? How well has it been evaluated? So they're the kind of questions you might ask. If the answer to that is yes, then you might then consider, well, what's the computational cost associated with that development? What does a cost-benefit analysis look like? And is the additional cost worth it in terms of the extra capability that we have and the extra scientific questions that we might be able to address with that capability? And increasingly, I think with the models based on the unified model, computational cost is becoming a real issue. So then the question is, if the answer to that question is yes, we'll take the hit in terms of computational cost, or indeed we've been able to address any computational cost issues, then the question then is, how good is the component once it's integrated within in the Earth system model? What biases and other components are impacting negatively on its performance? How are biases in the component itself impacting on other aspects of the model? So again, that's the kind of assessment we need to do when we're integrating new developments into the Earth system. And these are summarised here in those 5 bullets. So really, it's just a logical, rational approach to deciding is something worth doing or not. Okay, so over the next few minutes then, I just wanted to present on some recent science highlights that we've, in terms of work that we've done that's contributed to the 6th assessment report using UKESM 1.0. So the first example I've unashamedly taken from a paper of mine that was published earlier this year, where I looked at the impact of changes in methane over the historical period and quantify the impact on the Earth's radiation balance. We know from multiple models that there's a large uncertainty in the impact of methane on the Earth's radiation balance, and that's partly due to the representation of chemistry in the Earth system models that contributed to that assessment. So some of the models that would have contributed to CMIP6 didn't capture all the processes that would have contributed to those green bars, if you remember, on that bar chart. But part of the uncertainty in the methane forcing is also due to a response in clouds. So what we found in the UK's Earth system model, that when we perturbed methane in the pre-industrial atmosphere, we altered the oxidizing capacity, and that altered then our secondary aerosol formation, and in particular the aerosol size distribution. And that then altered the ability of the aerosols to perturb the cloud properties. And in this case, the clouds became less reflective, and so it added an additional positive contribution to the radiative forcing from methane. The second example I was going to show is from a paper by Gillian Thornhill that was published last year. And this is where she quantified a range of what we call biogeochemical feedbacks. So, for example, if you have a change in climate within your Earth system, how do natural processes then respond to that change in climate? And does that change in those Earth system components themselves then give rise to an additional change in radiative forcing? So it's to quantify how different biogeochemical processes respond to climate change and how those responses themselves influence further climate change. So anything to the right of this zero line is what we refer to as a positive feedback. So if there's a little bit of climate change, for example, methane emissions from wetlands will increase. That increase in emissions will drive an increase in the methane abundance in the atmosphere, and that will give rise to an additional positive impact on the Earth's radiation balance. And here you can see a range of biogeochemical feedbacks covering aspects of the aerosol phase and the gas phase. And you'll see, for example, that this wetland methane feedback is the strongest and most positive of all of these feedbacks that were quantified. And of course, getting a handle on the magnitude and even the sign of these feedbacks is really important in terms of projecting what future climate change might look like. And of course, you'll see that there's quite a bit of uncertainty in some of them, even in the sign of what the feedback is. And the final example is some work that Stephen Turnock in my group has done, in which we've tried to quantify, if you like, what are called co-benefits and trade-offs from different mitigation pathways. So what we've done here is an assessment of the impact on climate through assessing radiative forcing, but also the impact on air quality from different mitigation pathways. And the kind of pathways we looked at were changes in aerosol emissions, changes in land use, changes in methane, and so on. And the different colours here refer to these different pathways. And what we've done in this plot here is the y-axis here is the impact of these mitigation measures on the Earth's radiation balance. So it gives us an indication of the climate impact. And on the x-axis, in this plot on the left, which is for ozone, is showing the change in the number of days of this ozone metric that relates to a World Health Organization standard. So anything positive here is an increase in exceedance days, so representing poor air quality. Anything negative here is representing an improvement in air quality. So this quadrant here is representing what we might refer to as a win-win, because the measure is giving rise to a negative change in the Earth's radiation balance and a reduction in exceedance days. And so what we can see is that if we reduce methane in the atmosphere, or if we include methane alongside reduction in aerosols, we can get a win-win for climate and air quality, both in the context of ozone, but also in the context of aerosol. And really, our government sponsors are really keen on having quantitative advice on the impacts of different mitigation options, and in particular quantifying some of the trade-offs and co-benefits that we might get. So likewise, if we were to consider, for example, low aerosol here in blue, you can see that although there is a reduction, a benefit in terms of air quality in reducing aerosols, it does come, there is a climate trade-off because the change in radiative forcing ends up being positive. So again, it's important that we quantify some of those trade-offs as well as identifying benefits. Okay, so just to wrap up then, and I'm well within time, I'm hoping by now you have a good understanding of what we mean by the Earth system and how models have developed over time from very simple atmosphere or ocean-only models through to more full representative Earth system models. I hope I've given you a good indication of the importance of including some of these Earth system components in the context of climate change. I briefly outlined our current capability in terms of the UK's Earth system modelling and our plans for our next Earth system model. And I should say all of these are based on the Met Office Unified model as its atmospheric component. And you'll hear later on about the ELFRIC model, which is the next generation atmosphere model that will be used. And it will be UKESM 3 that will be built on that ELFRIC model. So that's still some time off for us in terms of the Earth system. And then finally, I finished up with some recent Earth system highlights where we've exploited the capability in UKESM 1 to look at some interesting science questions. So thank you very much for listening, and I'm happy to take questions.
Thanks, Fiona, for a great talk. Any questions?
You mentioned when you run the model from UKSM 1.0 to 1.1. You mentioned that you are doing some retuning. So that's how many parameterization you are changing, or we just change one or two?
Oh, I don't really know because I wasn't involved in this retuning. I think it was probably quite limited in extent, I think. So really the focus was very much on the aerosol side in terms of reducing the burden of sulfate and reducing the radiative forcing associated with it. So, I would refer you to this discussion paper if you were interested in the details of the retunings. Yeah.
I just wonder that what do you think that we can apply the UKCA that it says like model, right? Especially for the carbon cycle. I'm interested in that part, and also I mean that you talk that there's the emission is mainly from fossil fuels and land use, and there's ocean, land, and atmosphere that absorb it. Which one that you think that we still need to taking deeper understanding on it?
So at the moment we don't have a huge amount of interaction between the terrestrial carbon cycle and UKCA. That will partly change with methane emissions-driven capability, because that, once methane is oxidized fully in the atmosphere, that will generate CO2, and CO2 itself will be emissions driven, so we won't be prescribing concentrations of CO2. So we will start to increment CO2 in the atmosphere from methane oxidation. Now, having said that, the fluxes of the production of CO2 from the oxidation of volatile organics will be quite small relative to the CO2 primary sources from combustion. So that's one example. I guess the other example of interactions that will come through interactive fires, because that's, again, the vegetation distribution will be determined by the dynamic vegetation. Fire then will cause that to be removed or damaged, and there will be both emissions of CO2 from that, but also then emissions of other trace gases, like carbon monoxide, for example. So that again is another interaction. We do also have an interactive biogenic VOC emission scheme that I didn't mention here, but again, that the emissions of those VOCs are sensitive to the vegetation type, but also are sensitive to CO2 as well as temperature. So there are interactions there. I'm not sure. Has that answered your question?
One of the slides, you mentioned the uncertainties of predicting methane itself and interactions with aerosols and clouds. How do you compare those uncertainties?
So my paper breaking down the methane forcing was able to break it down into how much was due directly to methane, because that methane is a greenhouse gas itself. I was able to quantify how much was due to methane-driven perturbations to ozone, likewise methane-driven perturbations to stratospheric water vapour, and then I was also able to quantify the cloud forcing. And it was unclear from a multi-model study that had been published by Gillian Thornhill how much of the discrepancy in between the models was due to chemistry and how much was due to cloud. And indeed, some of the models had quite a low estimate, and they tended to be the models that didn't have interactive chemistry. So they were only getting, if you like, the methane direct forcing, but missing out on that ozone and stratospheric water vapour. There also appeared to be a difference in the models between the cloud forcing. So, and again, part of that may come down to capability, because there were only 2 of the models that included interactive chemistry coupled to what we call a 2-moment aerosol scheme. All of the other models either didn't have interactive chemistry, or their aerosol scheme was a mass-based scheme where the size distribution is fixed. And the 2 models that did have the capability of chemistry coupled to a 2-moment scheme, both of those models showed a positive cloud forcing, so increasing what their forcing was. But the UK model had a particularly strong cloud forcing. And I do think we're probably very our aerosol size distribution is very sensitive to the flux that goes through that SO2 plus OH reaction to form gas phase sulfuric acid, which then nucleates. I think we're incredibly sensitive to that, and I would suggest that maybe our cloud forcing in this instance was probably too strong.
The uncertainties are only based on how much models differ in the results. It's not really that you have measured.
So for example, for the methane part, we've been able to compare with a much more detailed line-by-line radiation code. And actually, we think that direct component from methane itself is probably less uncertain than the others. And that's partly because we were prescribing the methane concentration, so there was very little uncertainty in what that change in concentration was. So I would say that component is probably well constrained. The methane-driven the contribution from ozone then is very much model derived, and there will be some diversity across the models in terms of what those ozone changes are. And again, our model probably seems to be sensitive to methane, but other models would have modelled the stratosphere but excluded the tropospheric components. So some of that model spread, if you like, was very much down to representation of chemistry. But the cloud, I think, clouds generally are very uncertain across the board. So I think there are different components and they have different levels of uncertainty. So what it's saying is that as we warm up the climate, so as we warm up the climate, we get lots more water vapor. So we can actually increase the amount of ozone destruction that occurs in the troposphere. So we anticipate that background levels of ozone in a warmer climate will be lower in the absence of emission changes, because we're making the atmosphere warmer and wetter. That's what I think there. I think, anyway. Thank you.